past 6 months, I've been building programs and algorithms for quantum computers. And one of the most interesting things that I've learned is that quantum mechanics is really strange. If I were to throw this clicker across the room right now, you could pretty easily guess that it's going to hit the ground. But if I had a quantum mechanical clicker with quantum properties, there's actually a chance that it would never hit the ground and it would end up on the roof or something. Let me explain what I mean. So imagine a tennis court with a giant wall instead of a net. And in the middle of that wall, there's two slits like this. And on one end of the tennis court, there's a canvas. And at the other end, there's a tennis ball launcher with blue painted tennis balls. If you turn on the cannon, you could pretty easily guess that most of the balls are going to bounce off the wall, and some of them will get through and leave these two clusters of blue dots on the canvas. Now, we actually did this experiment in real life, except we used electrons instead of tennis balls. Now, you'd probably expect a pretty similar result, but what happened in reality is very different. We got this strange pattern with dots in the middle and off to the sides, and really in places that electrons really shouldn't have been able to hit the canvas. So scientists were pretty confused when they saw this. So what they did was they added these detectors near the wall and to see if they could figure out what was going on in the experiment. And what's really strange is that when they added the detectors, they actually changed the results of the experiment back to the original two clusters. So somehow, by simply observing what was going on in the experiment, they changed their results. Now, as the electron is approaching the wall, it turns out that it hasn't actually decided where it truly is in 3D space. It could be here, but it could also be over here. It's probably right here, but there's also a chance that it could be way over here. And so this pattern that they were seeing was actually all of the possible locations that the electron could have been in. And so how does that make any sense? Well, as the electron was approaching the wall, it suddenly decided that it was going to be in this location. And so when it hit the canvas, the universe kind of forced it to take on that position, and all the other ones were eliminated. We can make this a bit simpler by focusing on just a single electron. Now, that electron is in a quantum state, which means that before anybody's looking at it, it's actually in a combination of all of its possible states at the same time. Now, if we use that electron as a single operating bit in a quantum computer, we can actually have it in multiple states at the same time. So instead of being in 0 or 1, we can actually have it as a combination of 0 and 1 at the same time. And so we can actually perform several operations on the electron in parallel and then measure at the end to get the result almost instantaneously. So let's say you were trying to use a computer to find somebody's phone number in the phone book, if those still exist. Now, on a classical computer, you'd have to run through the entire list of names, performing an operation on every single one before you found the answer. But on a quantum computer, we could actually encode those names into just a few electrons, perform just a couple operations, and almost instantly come up with their phone number by performing a measurement at the end. Now, exactly how we do this is pretty complicated, but just pretend, for example, that it is possible. So this is actually only one example of the power of quantum mechanics. I'm personally a lot more excited about quantum simulations. Quantum simulations, it turns out that quantum computers have this crazy parallel probabilistic nature that gives them a really good ability to simulate our universe. And what that means is they can actually completely accurately predict the complex behavior of entirely virtual molecules. And although this seems really abstract, it has some pretty mind-boggling applications. For example, on average, the current drug discovery process takes a minimum of about 10 years. But with a quantum computer, we can actually simulate drug molecules and come up with a cure in weeks or even days. And what that means is in the time that it takes a human to discover a cure for a disease, a quantum computer could find dozens. Now, the other thing that quantum computers give rise to is nanotechnology. If we can properly harness the effects of quantum simulations and quantum mechanics, then we'll be able to simulate and design extremely precise nanomaterials on the molecular level so that we can create anything from oil-eating nanorobots to spray-on shoes, which is personally one of my favorite nanotechnologies ever invented. When I was working at the Creative Destruction Lab this past summer, I was focused specifically on quantum machine learning. And again, quantum computers have this really probabilistic and parallel nature, which gives them an unprecedented ability to process machine learning algorithms. And so not only are we seeing a speed up in machine learning processing times, but we're also seeing a capability to run models that have never been possible on classical computers. Now, I want to finish off by revisiting the experiment with the tennis court and the electron. The one thing that I didn't mention is actually the most interesting part, but it's also the hardest to wrap your mind around. So like I said, when the electron is approaching the wall, it's in a quantum state, which means that it's in a combination of all the possible locations that it could be in simultaneously. But when it hits the canvas, the universe is forcing it to take on one of those positions. And the question that I'd ask you to think about is, what happens to all the other positions? And the truth is, we don't actually know. But there's a very real possibility that every time we observe a quantum particle, the universe is actually splitting off into alternate universes where the particle appeared in this location rather than that one. And so there could literally be hundreds of thousands of universes where a particle appeared here rather than there. And the implication of this multiverse theory is that by creating quantum computers, we're essentially tapping into the computational power of alternate universes to solve problems in our own. 1,000 years ago, people relied on horses to get everywhere. And they couldn't even conceive of traveling beyond where their horses could take them. But today we're talking about sending rocket ships to Mars. And that means that we're not only traveling to places beyond where their horses could take them, but to places that they would call alternate dimensions. And so the classical computers of today are kind of like the horses of the previous millennium. And by creating quantum computers, we're literally tapping into resources that humanity has never even conceived of using.